Okay, so just looking at activity 7a, I'm going to go through the questions one at a time to make suggestions on how they can be solved rather than going through them completely in this video. So question 1, you have a crane used to raise and lower an iron bar, and the cables are at right angles, so it means we can do some vectors later. At one time, a number of bars with a mass of 210 kg are accelerating vertically upwards at 0.15 meters per second. So we're getting some information here. It says up here to use G equals 9.8 meters per second. And we've got the mass that's being accelerated, and we've got an acceleration given. So the first thing is to think, if I've got a mass being accelerated and I've got an acceleration, that means that that's the result of an unbalanced force. And the first question is to find the size and direction of the unbalanced force. So the appropriate equation, F equals ma. Now F is a vector and so is a, the acceleration. So in this equation, they're the only two vectors. That means that the force and the acceleration must be in the same direction. Same direction as the acceleration, and the mass, and the size of the force can be found using the equation. 1b says calculate the total upward force that must be acting on the iron bars. Now this is getting you to think about that up here, this force here that's creating this is the net force, so F net. And if we think about what F net comes from, the F net vector, that comes from the vector addition of the other forces involved. Now on the bar, if we think about the forces on the bar, let's assume that this string here, or this rope rather here, this rope here, and the bar, let's just treat them all as one. So in our system we'll have a upward force from the tension on this main rope here, and the other force that we're going to have is a downward force from gravity acting on the bar. So F down equals F of gravity, which is m times g, and F up equals the tension from the rope. The tension in the rope. Now the tension in this main rope up here at the top, that is the total upward force. So F up equals F net minus F down. Now it's not quite right, is it? What I've actually got is I've got directions here, so these are in different directions, opposite directions in fact. What we need to think is that overall we're looking for an F net that is positive, is higher, is going to be added on, because what you've got is the force from gravity pushing down, but the actual acceleration is up, which means that the upward force on this main rope here must be higher than the gravity force. So let's add the two together instead. And that accounts for the differences in direction. So F net was up. So let's make up positive. In that case, the force up is positive, but the force down is negative. Therefore, when we switch this to the other side, we've got add F down, and so we get F net plus F down. So that makes sense now. Okay, so thinking about direction as we go, if we set a direction as being positive and another direction as being negative, then we can make this work. Well, we can make the equations work for us. Okay, part C. Name the individual forces acting on the iron bars to provide the upward force. Okay, so the upward force is coming from this rope here, but they're not acting directly on the iron bar. The forces that are acting directly on the iron bar are tension 1 in this cable and tension 2 in that cable. So tension forces in cables T1 and T2. That's kind of the answer, so you don't need to do any more about that one. D. If the two cables attached to the bars have angles as shown in the diagram, draw a vector diagram to show how the two tension forces T1 and T2 acting on the iron bars combine. Now this is again, and this time what we've got is how do they combine? Well, they combine into the ultimate upward force, because that's where those tension forces. So what we've said in part C is that the individual forces that provide the upward forces come from T1 and T2, but they combine to be this F up in this rope here. So we've got to have an upward arrow as our F total. And we'll put a second arrowhead on it to show that this is going to be the resultant, and it's made up of tension 2, that's this one here, and tension 1, that's there. Now, can we remember how to do vector addition? That's nose to tail, and we have to get to the point where we get a nice vertical line here. Okay, so there's your vector diagram showing how you get the two forces, T2 and T1, to combine to be the total force. E. Calculate the sizes of the tension forces T1 and T2. How do we go about that? Well, we're given, firstly we have to actually go through, we'll have worked out by now what the total upwards force is, the magnitude of this. We've been told some really useful information, that they're at right angles to each other, and then we can use our trigonometry. We've been given some angles to work with, which we can use to work out the that this angle here, for example, is 145 degrees, which means this angle here is 35 degrees, and that leaves 55 degrees up here. So now that you've got some angles and you're going to have a total upward force from a previous part, you have enough to solve for T1 and T2 using Soa katoa. Okay. Let's have a look at question 2. A child pushes a toy trolley along a horizontal floor. The trolley's handle makes an angle of 40 degrees with the horizontal, and he pushes with a force of 5.5 newtons down the handle. Okay, so the force is down the handle like so. Draw a diagram showing all the forces acting on the trolley. So let's think hard about the trolley. It's going along a floor, right? Along a horizontal floor. So forces we need to consider: the force of gravity. That's, which direction is that? It's down. Support force. Which direction is that? It's up. Can the support force apply a horizontal force to the trolley? And the answer is it's a wheeled trolley. We're going to assume that it's frictionless, I think. And the other force being applied is the handle force, and that is shown here already. It's coming down at the angle of 40 degrees. Okay, so if we're asked to draw a diagram showing all the forces acting on the trolley, our best protocol is to draw just a box, dot in the center. We're going to run all our forces from there, and we're going to have them running away. Fg, down, Fs, support, and the force of the handle, the force through the handle, heading down that way. So it was A. B, calculate the size of the force component pushing the trolley along the floor. So this is our trigonometry again. This is about breaking out our pushed force, 5.5 newtons, into two components. Here's the angle given, 40 degrees, and the component along the floor is this one, F along. And we're also going to, part C, have to calculate the component that is into the floor, we'll call it F into, and you're going to use SOHCAHTOA to find those. You have the length of the hypotenuse and the angle, so that should not be too hard. So that was B and C. We've got part D. The mass of the trolley is 0.75 kilograms. Calculate the gravity force on the trolley. F equals mg to do that. And part 2, calculate the size of the reaction force on the trolley. So this is going to be F vertical, or F support rather. So if we think about our forces here, we've got to look at the vertical components involved. So the support force is going to equal the gravity force plus whatever the vertical component of the handle force is, the F into the page, which is going, so arrow that way actually, isn't it? Okay, so F into plus F gravity. F support equals F into plus F gravity, the weight force. Okay, let's spin this around to look at question 3. A crane is being used to raise and lower, we've done that one, what am I talking about? A car of mass 955 kilograms ran out of petrol when it was travelling with a kinetic energy of 93,600 joules. The driver knew there was a petrol station further ahead, and so let the car coast along the road as far as possible. At first the road sloped down and the car gained some more kinetic energy. Calculate the speed of the car in meters per second when it ran out of petrol. Okay, so it's a timing question, so we've got runs out of petrol at instant 1, and then at some point later, instant 2, it has some more energy, and then something else is going to happen. Later on in part D, the road then started to go uphill and the car eventually coasted to a halt after it had gained a vertical height of 11 meters. Point 3. Okay, so let's have a look at these things. It's clearly a energy question. I mean, it's really talked about kinetic energy, and I can see some gravitational potential energy type stuff coming in. Calculate the speed of the car in meters per second. All right, our units are in kilograms and joules, so this should be quite straightforward. It's really asking you about the kinetic energy, which equals a half mv squared. Okay, you can use that equation. You're given the mass and you're given the energy, so you can work out the velocity v. Convert this speed to kilometers per hour. So if we have a speed, let's just call it 1 meters per second for now, and we want to convert it into kilometers per hour. So 1 meters per second equals, and how many meters in a kilometer? So a meter is 1,000th, 1 times 1,000th of an hour, and 1 second is 1/36 thousandths of a, so this is 1 hour divided by 1,000 is the meters, and the second is 1/3600th of what am I talking about? A meter is 1,000th of a kilometer. Sorry. And the second is 3,600th of an hour. Okay. So 1 meter per second equals 1 times 1 over 1,000 times, now 1 over 3,600 is the same thing as 3,600 over 1, and the hour ends, so the kilometer was on top and the hour ends up underneath. Okay, and overall we get 3.6 kilometers per hour. So 1 meter per second equals 3.6 kilometers per hour. Now let's just think about that. If you're traveling at 1 meter per second, you're traveling at 3,600 meters every hour, which means you're traveling at 3.6 kilometers per hour. So if we want to convert from meters per second to kilometers per hour, we can multiply by 3.6. Or you can go through this kind of convoluted thought process every time. Part B, calculate the momentum of the car when it ran out of petrol. Well, you've calculated the velocity. So you have velocity from A1. Therefore, just use P, which is momentum, equals mv. Momentum equals mass times velocity. Part C, calculate the maximum vertical height the car dropped as it coasted downhill. It's interesting it talks about maximum. So it's assuming here that there could be sort of friction using up stuff as well. So I think that's right anyway. I'm not quite sure. I would have thought it would be the minimum vertical height. I'm not sure why it's used maximum. In any case, what we're going to do here is assume that there is a change in kinetic energy and that is equal to a change in potential energy, okay, which is a usually true thing. In this case, delta EP equals m times g times delta h, the change in height. So the change in kinetic energy here is given in the question. At first the road sloped down and the car gained 37,500. So 37,500 equals this. You've got the mass, you've got the gravity, you can work out the change in height. Part D, one last tip here. The road then started to go uphill and the car eventually coasted to a halt after it had gained a vertical height of 11 meters. Calculate the gravitational potential energy the car gained as it coasted uphill. So again, delta EP equals mg delta h. Now that's going to give you an energy that has been lost from the car, converted into lost from its kinetic energy and converted into gravitational potential energy. But we also know that its total change in energy in this case, the total change in EK equals, and we're given two values, 93,600 plus 37,500, and that equals this change in height, or this new change in EP from here, this one, plus whatever it is that's been lost in friction. So we've been asked to calculate the work done by friction to bring the car to a halt, plus work from friction. Okay, so the friction losses plus this energy that's converted into potential energy, gravitational potential energy, must between them consume all of the kinetic energy that the car had before it started going up the slope. So that brings us to a halt of looking at these and giving you some tips on how to solve them.